very much for the kind invitation. So I was asked to give a lecture about the mathematical solution of the Liouville CFT. And I was told that most of you have different backgrounds. So I will take it easy. It's unusual, those who know me, it's unusual that I do a blackboard talk, but it's to take it slowly. So don't hesitate to ask questions. For Probabilist, I will spend some time trying to explain the probabilistic construction. So for Probabilist, I think it will be basic setup. Okay, that's life. There are two reasons why you want to study this model. So in physics, it's a well-known model. It was introduced a long time ago by Polyakov. They are also not introduced, but it popped up in the context of 2D quantum gravity or string theory. I won't discuss it at all. Okay, I'm more interested in the mathematical aspect here. And what is nice for mathematicians in this setup is that this CFT, it has a continuous spectrum of Virasoro representation. And I will present how probabilistic and analytic methods can solve this problem. Okay? That will be my main focus today, or at least this week. Okay, so basically, just formally, just to present what I will want to talk about. So we are trying to solve a CFT. It has a Lagrangian description. This means that we are trying to construct a formal integration measure in the sense of integration. So, and this integration measure, it runs over the space of maps, whatever this space is precisely. It runs over a space of maps defined on some Riemann surface sigma, taking values into R. Okay, so phi is a scalar field. On my Riemann surface, I have a metric, a Riemannian metric G, and some geometric some geometric objects associated to this measure. So here it's the volume form on my manifold. Here, this is the Ricci scalar curvature on this surface sigma. If you don't know what G is, not big deal. And in this action functional here, you have three parameters. So mu is just a positive. It has to be positive, but you don't care that much about that mu because the theory has a scale with respect to mu. Okay, so basically you can think of mu equal to 1. Q is a function of gamma, and gamma is a parameter between 0 and 2. So in math, we are stuck to these values for now. There are other values that were discussed last week and yesterday, but okay, these are different theories. For now, I will be stuck to gamma between 0 and 2. Okay, so the main goal is to define first this functional integral. Okay, and this f here is just a test function that you have a measure, you evaluate the function. Okay. Questions?
Involve derivatives of phi?
Sorry?
Can you involve derivatives of phi in this big F expression?
Does it involve the representation of
derivatives of phi?
Well, you can take any functional of phi here, you just evaluate it. You can take any functional of phi, yes. But here, yes, so that will be important. The action has to be local. So meaning it can involve derivative of phi, but only finitely many of them. And so here, this expression, it's a really local expression. Is this what you have in mind? It's more important that the action is local. That this f, you can take whatever reasonable function you want. Reasonable means if you're a mathematician, you have to take a measurable function. Okay, so we have this functional. So it defines usually you note it this way. So this means for expectation values with respect to this measure, and this object depends on the Riemann surface and the metric that you have put on it. What you want to do at the very end of this story is that you want to introduce some vertex operators. So basically, they are just exponential of the field. You evaluate them at a point on the surface. You form this product of various vertex insertion, and you take the expectation values. Okay? You want to compute these quantities, and well, in a reasonable way. There are many ways to compute these quantities. Reasonable means that we are trying to connect with the representation theory in a little bit, at least. Okay, and so what I will explain more or less, the plan will be more or less the following. I will start with one. So this is only a probabilistic object. I want to connect to the formalism of CFT. So I will use something that was, well, in math, it was designed by Segal. I think that the story is way older, but I will start from here. So Segal gave a definition of CFT that is super well adapted to the Lagrangian description of a theory. So I'll try to explain a little bit the philosophy. Then I will give you the expression for the structure constants. And then I will play with Segal. You will see that there are a lot of things that you can reconstruct from the Segal axiomatics. There will be the semi-group, a special semi-group of operators that you can form. And from this family, from this special semi-group, you can extract at least two objects. So there is the Hamiltonian of the theory. So Hamiltonian is a special operator because from this semi-group, you can construct a representation of the Virasoro algebra acting on some Hilbert space. There is a special operator in this family of operators that in this representation, and the special operator is the Hamiltonian, and we will see, and this is really the core of the analytic aspect. This is a spectral resolution of this, well, the spectral analysis of this operator. Okay, this is really where things might be a little bit different from what you do in the VOA. Then we will use Segal to see that the correlation function, they can be decomposed. So we will play with Riemann surfaces. We will decompose them into basically into pair of bands. And once you have decomposed into pair of bands, you will have by Segal operators associated to this pair of bands, and we'll see how you compute the matrix elements. So matrix element means that you will plug the eigenstates of this Hamiltonian into the operators associated to the amplitudes, and you will try to compute them. And then I will give you an example of how to implement the conformal force. Well, that's more or less the plan. Today, I will focus on the probabilistic representation. So let me discuss. Well, first, I will explain a little bit the philosophy of the axioms. So what we will have, we will have a bordered Riemann surfaces.
Sorry, it's a language question. So when people talk about the Lagrangian description of the theory, it's this integral. When people talk about the Lagrangian description of the theory, they're talking about this integral description, right?
Yes, well, yes.
And then the Lagrangian.
Well, the correct word is more or less the path integral. So I will have this action. Sometimes, well, physicists they call it the Lagrangian description in some way, but I will try to construct the path integral. So I will. So this G phi here, it's a formal Lebesgue measure on some space of maps, and I will try to weight the sampling of my phi with this exponential of the action. Okay. So So now I'm trying to explain the Segal philosophy, and then I will explain why it was motivated by a path integral description. So in Segal, you have a border Riemann surfaces. So there are two colors. I will explain later why. So you have circles here, and in between you have a surface, a Riemann surface. I can even have holes in between mark points. Okay, so this is a Riemann surface, and you have several boundary components. Each boundary component, so it's you have an analytic boundary, and each boundary is parameterized. By a map, so I will call it psi, that goes from the circle to this boundary component, to that C. So this is sigma. Let's call it. This is the first boundary component of sigma, and psi1 maps to. It's an analytic map that goes from the circle to this boundary circle. So this is the unit circle in the complex plane, and it gives you a parametrization of this boundary component here, and you have such a psi for each boundary component. And on your surface, you have an orientation. Okay, the surface it's a Riemann surface, so you have an orientation, and so it gives you an orientation of the boundary. And this map here, basically, it has two possible orientation depending on which way you go along the circle. So it gives you two different possible orientation for the circle, and this orientation may or may not agree with the orientation given by the surface. Okay? So if it disagree, we call it in this boundary component, and the red colors are for these boundary components where the parametrization disagree with the orientation of the surface. Okay, so in Segal axiom, so you will have an Hilbert space. So for now, it's a general setup. If you want to prove that you have a CFT, in some way you have to specify this data. Okay, so you have an Hilbert space, and you will attach a copy of this Hilbert space to each boundary component. Okay, and for Segal, basically, a CFT is a map from this picture. So to each. Well, I won't give you a precise statement, but to each such picture, it associates a Hilbert-Schmidt operator. I will call it A. So A is for amplitude. So it depends on many things. So it depends on the Riemann surface that you have, the matrix that you put on it, the mark points. So the mark points, it's a collective notation, this X for all the mark points that you have on the surface. There will be some weights attached to each mark point. Then there might be several of them here. And the weights are basically this alpha that you see up there. Okay, and it depends also on the boundary parametrization. Okay, and this operator, it's a map from the tensor product of the Hilbert space. Here is the number of in-boundary components. So here it's only one. So you have one copy of H. So it's an operator from H to H tensor out. So it means that here you have, in this picture, you have two out boundary components. So it's H tensor H. Okay, and so there are these maps, they have to obey some rules. I won't list all of them, but the main rules are the following. So first, this amplitude, they have to be invariant under diffeomorphism. It means that if you have a map, a diffeo psi from sigma to psi of sigma, the first rule that you have is that the A of sigma G X alpha psi is the same as the, so you have to push the metric G on sigma to this surface here. So I don't know where you put the star. I think for the push it's on top or right. Okay. Anyway, you push the metric G, you push the points. You keep the weights and you push the parameterization. Okay, so it's side. Okay, so this is the diffeomorphism invariant. Yes. Down. So this is the first rule. So that's something quite natural. Okay, it just means that your theory does not depend on the chosen parameterization. Okay, that should be valid for anything. Something that is more related to CFT is the following. So the way invariance relates to local change of scale. So it means that if you consider another metric G prime on your manifold sigma that is conformal to G, so it means that the metric G prime is just G times a positive function. Okay? It's exponential of some maps, smooth map defined on your manifold. Okay. Okay. So if you look at A of sigma G prime X alpha psi, it has to be equal to so there is a number in front. I don't remember the. Well, 96 pi is just normalization. So there is a constant here, a number CL times a special functional on your manifold, which is called the. Actually, it's called also the Liouville functional. Then you have a product over all the marked points. So M is for marked points. Those guys are the marked points. And then up to these two factors that are completely explicit, you have the same amplitude. And these two numbers are okay. CL is what's called the central charge. CL here. And the delta alpha are the conformal weights. Well, for now, if you don't know what this is, well, this is just a number that characterizes the universality class of your CFT, and this delta alpha are some numbers, complex numbers attached to each of such. Well, here it's it's called vertex operators, but okay, it's just at some weights, some numbers attached to this operator. Okay. Okay, that's two rules, and there is another important rule that is called the glowing rule. Okay, so far questions.
So delta is a function of these alpha or complex numbers.
Yeah, it's a function, but it can be any function. It depends on the labels. It can be anything. Okay, and the main rule. So the main rule, I will say it a bit informally, but I think it's easy to understand. What were my colors? My colors were blue. Yes.
What is the variable in the integral on the exponential after the 2RGW?
Here?
Yes.
2RGW, and then you have the volume form. So you compute this guy here, and you integrate over the benefit. Other questions? Okay, and then what you want to have is that this amplitude, they behave well or naturally when you glue the surfaces together. Okay. And so this means that if you take two surfaces, so let's take two bordered one circle. So you have the first Riemann surface sigma 1. Okay, and you want to glue these two surfaces. The sigma 1 with another one, let's say. Okay, let's do it. Simple. Again, you have sigma 2. May have mark points. Okay. So here you have an operator A sigma 1 with all the possible data, meaning the metric, blah, 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 the parametrization. Here you have sigma 2. And this guy is a map from H star 2 to H. This guy is from H to H. And Segal axiom, they say that if you glue the Riemann surfaces, say along this this boundary here, okay, you will get a Riemann surface. There is only one. One pole. So here sigma is the gluing of sigma 1 with sigma 2. There are mark points here and here. Okay, you want this amplitude. So you glue along the boundary component, and why it's important to glue in boundary component to out? Because if you glue in and out, you preserve the orientation of the surface. Okay, so this surface. So you can do the gluing according to the boundary parameterization, and what Segal tells you is that the amplitude of the glued Riemann surface is equal to the composition of the amplitude in the right order. Sigma 1, yes, okay. Okay, so this is what you expect, okay? And so you compose the operators according to the boundary components you do. Okay. Well, this is what you want. So is that clear? Yes.
You assume something about the regularity of the parameterization of the boundary?
It's an analytic one. Yeah. Perhaps you can do better if you have if you want to play with SLE curves, or perhaps doable, but for us it's analytic.
Okay.
But here you're assuming that you could always sew, there's never an obstruction.
Sorry?
You can always sew, there's never an obstruction. to
Absolutely.
sewing.
For the sewing,
Yeah.
well, as long as you glue boundary components that are in and out, you glue according to the parameterization, it's possible in our system. We are not demanding regarding the smoothness of the parameterization, so it's okay for us. And regarding, well, actually we ask for the parameterization to be analytic, so you can just glue analytically these boundary components. There are some questions, what Kali said, perhaps, what is the optimal regularity you need here to perform the gluing? I have no idea.
But you need no scaling factor or something
Ah,
on the boundary
I skipped a few
details.
Yeah, okay. If you ask that point. So here, first, there are some technicalities here. So, for instance, this Weyler invariance is valid when the omega here is nice close to the boundary. So, for instance, you can take it 0 in the neighborhood. Okay, there are some conditions here. Okay, and for the gluing, you have to make the metric that you've got on sigma 1 and sigma 2, they glue nicely. Okay, so the gluing has to be smooth. Okay. Let's say it this way. Actually, what we ask in our paper is that there is one reason for this. For instance, you can ask in local coordinates the metric to be local coordinates close to one boundary. You ask the metric to be of this form. Okay. Why? Because on this form near the circle. So you local coordinate close to the circle. So you look at a chart close to the circle, because the circle is mapped to the boundary. Okay. And you ask the metric to be of this form here. Why? Because this is the cylinder metric. So you are just going to cylinder. It's easy to do. And you will say, well, it's a restriction, but it's not that much a restriction, because then if you have a more general metric under some conditions, then you can play with this rule to change the metric. Not your question, or you want something more?
Right, because to me, I mean, this has to do with the scaling operator for your Virasoro, the L0. So if you can always sew, then you're introducing what you would call a dilettante, where you can rescale so that you could always sew the boundary. Whereas even just in a regular world sheet VOA picture, you should have some kind of obstruction so that you cannot always sew. And this is exactly has to do with the
for now, here there is no
so
Virasoro stuff at all. It's just the composition of operator.
Maybe I don't know if I understand, but maybe it's contained the metric, what you're saying.
right.
There's a metric here. And
But if you can rescale the metric, that will, I
metric,
guess.
only thing you need is this guy.
I think maybe the difference here is that when you're doing it with VOAs, you're thinking of puncture is in the Riemann surface with local coordinates around the punctures. But here you have the boundary
Just
components
boundary
with parameterized. I think with parameterized boundary components, you can always do it. But if you replace the parameterized boundary components with the sphere, punctured sphere with coordinates, then I think
Right,
that's
so you have to cut off your tubes that they're finite. Can't have infinite tubes.
Yeah, you're just going to choose. Can you do it in the toilet with two? Okay. Well, the heuristics now. Why you want to do that? No, we started at when? 15. Ah, okay. Thinking I'm slow usually, but then I'm super slow.
You have to look at him for the time.
Yeah. No, just because we started later.
It's And then again, we moved the next one. It is 11:30, so we have a time.
we have time.
Okay, so for Segal, what are these amplitudes? So A of sigma G X alpha psi. It should be in some way. It should be given by this product of V alpha 1 X1. So this Xi, these are the points in infinity here. M fine. But here, so it's for those maps defined on the manifold taking value into R. You have your manifold here. But here you further ask the map phi to take on prescribed values on the boundary components. So it's yes. Okay, and what does that mean? It means that you will prescribe boundary values on your for your field on the boundary components. And so what are those phi? Basically, if you look at the path integral, here you have circles, you will just look at the restriction of your global phi on the surface. You will look at the restriction of this field on the boundary components. Okay, and you will impose some prescribed value. So if you look in coordinates, this phi I, there will be maps defined on S1. So basically trigonometric series function on the circle, taking real values. And so this is in coordinates. You map this function defined on the circle via the parametrization to the surface. And then you impose the field to be given by this phi I in coordinates on the boundary components. Okay. Okay, and why do you want to do this? Well, because if you have, say, a surface, and so, yeah, sorry. So what do you do with this guy? So your Hilbert space basically will be a space of maps of this phi defined on S1, taking values in the circle. Okay. You will have to put a measure on this space of maps, say, to make it say a Hilbert space. Okay, so you will equip this space with a measure. Okay, you consider, for instance, H to be the L2 space with respect to this measure. Will give you a Hilbert space, and then to each boundary component you can attach. So you have a copy of the Hilbert space. So given a copy, you can extract boundary components. So you will have phi 1 here, phi 2 here, 3 boundary components. And so you try to compute this path integral given this boundary condition. And why you want to do this? Because if you have a surface sigma that you cut with a curve, okay, to split your surface into 2 components, sigma 1 and sigma 2. If you look at the path integral, So if you want to compute this guy, here this is just an observable. It has a special form that special observable that I plug it into my measure. It's just that it takes a function of the restriction of the field to the first surface times another test function of the field restricted to the second surface. Okay? So if you're trying to compute this integral, if you assume that the action is local, so this is what you asked before, if SG is local, it means that you can split the action functional into two parts. Okay, so this is clear for the Liouville action. You just split the integral into two parts. Okay. If you have this, you can try to disintegrate this measure with respect to the value of the field along this curve C. Okay, so it's just a disintegration theorem. Here it's on an abstract functional space, but you may integrate over those phi defined on the curve. You integrate over the law of all the phi that are defined on the curve. You have to figure out what is the disintegration measure here, but you expect that it's again the Lebesgue measure on this space of maps. For now, it's a heuristic. Okay? There is no Lebesgue measure, blah, blah, blah. But, and here, when you split this SG into these two parts, you will recover A of sigma 1, blah, 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 with boundary condition phi, times the amplitude of the second surface with the data, with boundary component phi. Okay, and so what is it? If your Hilbert space is the space of maps defined in coordinates on the circle equipped with this measure, so this form your Hilbert space, here you are just computing the scalar product of two elements in this Hilbert space. Okay. So here, for instance, it could be L2 of maps defined on S1 times R defined equipped with this formal Lebesgue measure. This is what Segal had in mind. Okay. Then there are, of course, issues. So just one thing, how to relate to the composition is just because if you take the scalar product, you can take put one guy on the other side and it corresponds to the composition. If you identify H with its duals, it matches the composition rule I told you. So the problem here is that you are dealing with functional spaces. You have to clarify what are these measures and so on. But this is what Segal had in mind. And he proposed his definition, but then if you want to show that your model is a CFT in the sense of Segal, you have to check this actually. Okay. Yes?
How am I distinguishing between incoming and outcoming circles in terms of this integral?
Here there is no in-out, but when you cut, the choice of in-out is arbitrary. You can put in on one side or you can choose your cut.
I mean, in the axioms, you're supposed to be going from H tensor in to H tensor out.
Yeah, so actually, yeah, so for instance, you can put, when you cut here, you can choose any parameterization of your curve. So possibly you can take one parameterization where here it's.
So I think this one's fine. I'm talking about just up here, and it's just definition of this.
This one here?
Yeah.
So the in-out, you see it on the parameterization here. Because the XI, they are either they coincide or not.
Just because the A here, you view it as the integral kernel?
Yes.
You identify integral kernel
Yeah,
operators.
Okay. So let's take this. Let's make an example. So yes, with this one here. Okay. Let's say that this amplitude is related to this picture here.
Yeah.
So what you will see. So here you have three boundary components. One is in, two are out. And so your edge should go from edge to edge. And then you see this guy as an integral kernel. So A of phi. Well, this operator is actually it maps A of sigma. So there is phi 1, phi 2, phi 3. You apply phi to F. So okay, so you need to be to arrive in the tensor product of H 2 times. So you have two guys here, and how it is defined, just integrate with respect to phi 1, with respect to your measure, let's say mu 0, phi 1, whatever your measure is on your Hilbert space. Okay? So this is a real integral kernel. Okay, so yeah.
A question like when Saclay introduced this, I mean, like if you have in mind the algebraic construction of CFT that you have Virasoro symmetries or extended symmetries like W algebras and so on. Somehow you have to, if you want to do a general, let's say, define general CFT, how, for example, you include maybe something that looks like more complicated Hilbert space, like W or versus Virasoro.
I think it's better to discuss it when we'll do the semi-group of analysis. Yes.
Sorry, I did not understand what are the V alpha. Are these just values attached to
The V alpha, so in UV, it will be the exponential alpha of the field. Okay, in UV, it will be, at the end of the day, it will be this one for me. And in general, for if you take, if you look at any model, it will be something else. For instance, in the Ising model, it could be the value of the spin at some given point. This guy depends on the CFT you're looking at. Okay, these are the primary fit. Like this. Yeah. So now, how do you implement this in UV? There are a few observations. So if you, I will explain first what we do, because I don't want to give you the definition from scratch. I want to explain a bit more why you do this. So if you have your class integral, so I'm trying to see how I will play with this guy here to extract the definition. Okay. So in this trivial action, you have several terms. I remind that SG of phi okay, so because of this Dirichlet energy, so basically the philosophy is that if you are doing integration with your students, basically when you teach integration, you start from the Lebesgue measure, say whatever you want on any finite dimensional manifold, and then you construct any measure reasonable by taking Radon-Nikodym derivative, right? Okay, so in infinite dimension, here there is no Lebesgue measure. Okay, so you have to start from something else. And what we like in the setup are Gaussian measures. Okay, because they are well defined. And we start from a Gaussian measure, and then we play with it to construct more complicated objects. Okay, so here the Gaussian measure is here. This is for a Gaussian measure, you need a quadratic term in the action. Okay, so the linear perturbation won't be too bad. Okay, so but basically this will be a Gaussian measure, and then we have this nonlinear term. Play with it later. Okay, but for now I want to play with this guy to see what we are dealing with. And when you have this conditioning up there, you can always decompose your field phi into phi 0 plus p phi. So here it means that this guy is the harmonic extension of boundary values. So this guy here is well defined. I give you on the surface, I give you 3 boundary data. You can always compute the harmonic extension of this. Okay. This map here is a map that vanishes on the boundary. Okay. Why I'm doing this? Because the Dirichlet energy is well behaved with respect to this decomposition. It just these guys are orthogonal with respect to the Dirichlet energy. So you can write your amplitude up there in the case of Uville. Blah, blah, blah. You can write it as a your products. So what do you have here? So you split the Dirichlet energy. And then you have exponential minus 1 over 4 pi. I will put a sigma here. This is the extension, harmonic extension on sigma. Plus, and then I just plug whatever terms are left. Gamma phi 0. Okay, this term is deterministic. I can put it up. But what is convenient here is that this guy here, this Gaussian integral with respect to the maps that vanish on the boundary, you can interpret them in terms of the Dirichlet Gaussian free field. This is a probabilistic object that Antti talked about a little bit yesterday. And then we'll see that guy later. But for now, if I'm just focusing on that guy, this one is well known. Okay? I will explain how it works. I'm assuming that there are people in here that are not familiar with the Gaussian free field. Is that correct? Okay, so the Gaussian free field, the Dirichlet Gaussian free field, if you have a surface with boundary, basically it's so it was, I think, designed in physics in the beginning. So you want to interpret this quantity here and phi 0, and its restriction to the boundaries is 0. Okay. So this guy does, so just if it was a finite dimensional integral, what you would have here well, if it was a finite dimensional integral, you would single out this guy. You will write it as a minus for some positive definite operator.
I'm sorry, the amplitude here should be differentiating over what? The variation on the manifold or the?
Here, there is no difference.
VG is, GVG is the variation on the
No, but
manifold.
GV is just the volume form. I'm integrating over the manifold this quantity.
Okay.
VG is the volume on the manifold. Like you can think of the Lebesgue measure on the manifold. So you have the field. So here you have the gradient of the field. Here you have your product curvature times the function. Here some exponential of the field, and you integrate this function over the manifold. Good.
But then I should be integrating this whole thing over all of the field, all of the.
And then,
missing.
yeah, here, this is really, you're trying to figure out what is this measure here. You're really integrating something. And
You're just missing a D phi 0 at the top.
yeah.
I just was
you're right,
confused.
you're right,
Yeah,
sorry.
I thought, I'm fine. But you are missing. Yeah, you should be integrating.
Yeah.
This is just to integrate.
Yeah, sorry.
Okay.
So if this integral was finite dimensional, it's a Gaussian integral, right? You would try to spot this operator. This operator here, of course, it's the Laplacian, right? Because if you integrate by parts the gradient, the Laplacian. Okay, and so what would be this integral? You would have the determinant of A, so it's determinant of Laplacian that you take to the power minus 1/2 if it was finite dimensional, right? And then you would have the expectation value of F of a Gaussian field. Such that the covariance of this guy is the inverse of this operator. That would be the definition if this guy was finite dimensional. Okay, so here actually, well, the analogy. This is how we define the Gaussian free field. So here there are geometric Reisinger stuff to define this object, and so it's not easy from scratch, but I won't discuss this guy. You can define the determinant of the Laplacian. And here, what is this Gaussian free field? How you construct it? So you take a basis. Well, I do exactly as I would do for the infinite dimension. So I would take an orthonormal basis of delta G. Okay, I want to choose the positive eigenvalues. Of the Laplacian. So orthonormal basis, I take En, I call them En. Right? And then I would just expand along this basis. So I would take x of x, sum over n, En of x, the eigenbasis, divided by the square root of the eigenvalues. Okay, and if you so this is a series. Okay, but I forgot something here. And then I would put coefficients that are IIG random Gaussian. So IIG Gaussian variant standard Gaussian. That's good. In finite dimension, we would do exactly the same story. And if you compute the covariance, you expand the double series. Here, when you compute, so watch out if you're not probabilist that there are two objects here. This alpha n, there are random variables. So actually, they live on the probability space with a little omega. Okay, and actually, this guy depends on omega as well, but it's standard to skip this notation. It's a random variable. Okay, you don't like it. Okay, it's defined on some probability space, abstract space, whatever it is. And then you have some random variables defined on that space. Only those guys are random. These are fairly defined smooth functions. Okay, and I take a random series, just a series, but the coefficients here are just random variables. Okay.
Could you point to an easy source where this is written for the finite dimensional case? Because I have to admit, I would not recognize that you say this is the same as in the finite dimensional case. Probably I should learn.
I think
Scholz their buzzword or something.
For the GFF or just for this Gaussian integral? I think you take any lecture, the first, I think any lecture on probability, the first year, you have a chapter Gaussian vectors. Like, Gaussian vectors, they will explain how to compute Gaussian vectors. Okay, if you compute this expectation, so you take a double sum, here you will have an expectation of alpha n, alpha m. It's null if n is different from m. So you're just left with the sum of exponential alpha n squared. Alpha n squared is expectation is 1, and then you will have just the deterministic term divided by lambda n. Okay, and this is the Mercer representation of the green function. So this is really a Gaussian field whose covariance is given by the green function. Okay. And for some reason, actually the green function, you know that it behaves. So this is the green function. X, Y. No, it's more or less 1 over 2 pi times the log locally. And I like to get rid of the 1 over 2 pi, so there is a normalization. It's just to normalize the logarithmic correlation of your green function. So this is the part that I was afraid of with respect to VOA people. If you have questions, that's part of the plan that I'm stuck here for a little while. So don't hesitate.
So you can ask another very naive thing. So I know this a little bit more from the physics side, and then you have an I on the top, right? And people say that
where is the I?
An exponent, yeah. And then people say that sometimes that it doesn't matter, and then other people say that it matters a lot because in one case you oscillate faster and faster, in the other case it descends faster and faster. I mean, does it here play a role that you don't put the I? I mean, what is your opinion on this?
There's a big role is that
this looks more like thermodynamics to me, I mean, in some sense, because you.
Yeah. Yes, you're right. But here I will be really focused on the case where I mean, well, the case where there is no I.
Shall I make a comment? I mean, there is of course an old story in physics behind, right? So originally, to do quantum mechanics, you would like the thing with an I. And then in the development of quantum field theory, Lim, Jeffy, Osterwalder, Schrader, and so on, people have observed that you can start with something which is easier to define mathematically, which is statistical mechanics type things. And then there is a procedure called wig rotation to recover the story with the I from the story without the I, essentially. But really the true way to get it is basically what is known as the Osterwalder-Schrader reconstruction theorem, which basically says if the thing that you define here without the I satisfies certain axioms, as Remi can prove in this case, then it is possible to construct from it well, the space of states and operators or operator valued fields on it, which then satisfy the axioms that you want to have for a true quantum theory, so which say you intuitively think about as being defined but with an I.
So we are on the side without an I, and we simply don't. It is okay.
The point is, sorry, the point is that there is this picture where there is the I. There is an analytic continuation, whatever the argument, to a picture where there is no I. But the picture there is no I, it's way better probabilistically because you have a convex functionals where probability makes sense. Then if you are lucky, in some case, you can go back to the I. And for you, you can go back to the I. But here, there is this analytic bridge, and we are on the good side.
Good side.
Yeah. Yes, okay, so we have this random function, but it's not, if you are a little bit more familiar, so with this Gaussian fields, this one is not that well behaved because this series actually is, you may say, well, it's a random variable in which space? Actually, it's a random variable taking values in a Sobolev type space, but the index is negative. It's not a fairly defined function. Okay? It's not a fairly defined function. And so it's a random distribution, but not a random function. I like to think of it as a random function. You may think of it as a random function, but it's too irregular to be a well-defined function. Okay, and that's the trouble. But still, the point. So the outcome is that this integral is. So there is this that blah 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 expectation of f of xg. Okay. And the xg is the GFF. So now you can, it's a Gaussian measure, it's well defined. You want to plug in this action the linear term. The linear term is just the field xg integrated over the manifold against the curvature. That one is super nice. It's not a big deal. What is the big deal is the non-linear term in the Liouville action. It's the exponential. You have this guy here. And this is where really probability helps. Okay. So why is it a problem to define this guy? Just because it's not, as I said, this guy is a distribution. So how do you do exponentiate a distribution? Well, you're stuck with this if you use analytic methods, but there is a trick in probability. You can regularize your field. Regularize your field means that you take x. You modify with any reasonable modifier on your manifold. It gives you a field x epsilon, regularize a field. And then you take the regularized quantity because this field, once you have modified, it's a function of x. It's a smooth function on the manifold. Okay, so this guy, what you've gained with this modification, that this guy is a smooth field, so you can exponentiate x epsilon. But of course, what you want to get rid of is the modification, right? Okay. So the thing is that this guy, it converges when epsilon goes to 0. So this is a random variable, okay? This is a random function. you take its exponential, you integrate over the manifold here, so you get a random quantity. Okay? It converges as a random variable to something. So, as you're not that much familiar with the Gaussian fields, I won't explain Gaussian multiplicative chaos, but these are probability techniques, so it's based on martingale theory. You can play with the randomness to show that this guy converges. But there is something is that if you look at the expectation, my statement is wrong. If you look at this expectation here, this is a random variable, you can compute its expectation. Actually, this expectation is a further exponential minus gamma squared over 2. So it diverges. The expectation values of this guy diverges. So what you do is you tame by the mean value, and you're trying to see, well, does this guy converge? You use probability techniques, and you show that if gamma is small enough, okay, this guy converges. So this is why you see the restriction on gamma. This guy converges for gamma between 0 and 2 towards a non-trivial object. But when gamma is in this range, the limiting random variable is non-trivial. Okay. This is what Antti said you have to renormalize. This is because you need to tame a little bit this guy to converge. It's not super intricate renormalization stuff, but you have to do this. Okay, so the message here is that there are probability techniques that can make sense of this weird exponential of distribution. Yes.
To be sure I understand the statement precisely enough. I can think of the definition of the object which is regularized, so which has a finite value of epsilon, as being fairly elementary in terms of probability theory, random variables, and so on, the modes, right? But then somehow the main statement is basically that there is a theorem, the object that you have defined, multiplying some epsilon dependent factor, has a finite limit. So this is sort of the main content of this story of Gaussian multiplicative chaos.
Yes.
Basically in that theorem, so you start from something that in principle I can think of as being relatively elementary in its definition, and then there's a theorem that this object has this limit.
Yes. Yes. So the answer is yes. Then you may ask about. Then you may say, okay. Then what if I was about to say mathematician, but even physicists, you may say, well, okay, well, how can I be sure that it does not depend on the choice of the regularization? That's an important statement. And there is also a math theorem that this object is universal. Whatever the regularization, you get the same object in the limit.
It's the time. We don't stop.
Okay.
Excuse me. Yeah, you assume rho epsilon of x is some fixed function of x over epsilon. Otherwise, I mean, your statement is not very precise.
Say it again.
Rho epsilon of x, is it a fixed function of x over epsilon?
Yes. You take a modification, so if you're on the plane, you just take yes, something like that.
Okay.
Any bump function.
Okay.
This is not what you would do from scratch in probability theory. If you want, so this guy, it's natural, but for probabilists, it's not the most natural approach. What's the most natural for probabilists is just to truncate this series here. So because you are increasing randomness. Okay? If you stop at the n first level, n first harmonics, it's just a sum of a smooth function, so it's perfectly smooth. But the fact that you add independent functions tells you that this guy is a martingale. If this guy is a martingale, then there is a super nice statement that if you look at this measure, so this is the n means I stop at the first n harmonics. I started the questions, right?
Yeah, we start the questions.
So it's super easy to see that if this guy is a martingale, sum of independent random variable, this guy here, if it's a martingale, if you take its exponential, you just have to remove this guy to make it another martingale. Okay. Then the point is that this guy, for probabilistic argument, a bit more involved, you can show that it does not converge for each x. Okay. So what is you have to find another topology. Okay. Then so you say, okay, let's see it as a measure. So I will look at this random measure instead. So I have a martingale in the space of measures, and this guy it converges. Here, when you have a martingale, it always converges. Well, it's positive. Positive martingale always converge. The point is that if you just see it as pointwise guy, you're stuck. You change the space in the space of random measure. This guy, it's a martingale positive, and it converges almost surely. So this is a general statement, whatever gamma, and if you restrict furthermore to gamma between 0 and 2, then the limit is non-trivial. You have a random measure leaving, you have a random measure.
That's the actual way you regularize capital X.
That's one way, yes.
But I don't see the relation with convolution.
But that's a tricky one. Actually, you have one regularization, you have another one, and then this is a theorem that both of them gives you the same story.
Maybe one more quick question.
Is there some kind of intuitive reason why this limit is trivial, or when gamma is equal to 2 or 0 or some other value?
Okay, so you have a limit here. So when you get 0 in the limit, it's not that bad. You can just renormalize differently to get something non-trivial, hopefully. And the answer is always, you can always renormalize to make this limit non-trivial. So actually, but still, what is the limit? At gamma equal 2, there is a non-trivial object. If you further push by a square root of log epsilon. Okay. And the object is natural and non-trivial and so on. So there is something at gamma equal 2. When you are above 2, it's called the supercritical phase. You can further push by some powers of square root of log epsilon. And you get a non-trivial object in the limit, but it's slow. It's important. It's slow, so it's the supercritical regime. It's related to the subcritical regime by, well, not trivial, but almost trivial transformation, probabilistic transformation. This means that what you get above gamma equal 2 is related in a trivial way to what you get below. So it's not interesting. In that sense, actually.
Okay, maybe more question at coffee break. Let's thank Remi again.